Okay, in the last video, we were able to derive this area, the one in yellow, and we were able to plot this. Now, in today's video, we will be focusing on how to use the double area by double meridian distance method to derive the formula or the uh, lot area of this given technical description. Okay, so let's start. Now, as a preliminary to prepare this, okay, we're going to copy this plot and then paste it on our paint for presentation purposes. Okay, now, so we will be using this to derive the area by double meridian distance method. Okay, now, okay, let me pause to prepare. We will be interested in this, the respective latitudes and the departure of each line to derive the double meridian distance for each, and then multiplying it by the latitude to get the area for the respective lines, and then summing them up and dividing them by 2 to get the double area. So we will explain this as we go along, but for now, we will, to save space and to focus on what matters here, we will be closing this, hiding this to give more space for our paint for this area. To derive the formula for our lot area computation, we need to understand the word meridian. As you can see here, each line, in our last video, we were able to derive the latitude, which is a given line, and then the departure is the horizontal line for that given line. So in this example, this is the latitude. This is the latitude, and then this is the departure. And the meridian is the distance between this and this vertical axis. Okay, this is our departure, and then since this is the departure, and then we are interested in the meridian between the midpoint, the horizontal distance between the midpoint and the vertical axis, which happens to be the coincides with our latitude. Necessarily, this length is just half of our departure for line 1 to 2. Okay, so let's create a table. We'll go back to this, but we will explain the concept of meridian, so that when we go back here, we will know what is double meridian. Let's create another column for our, we'll call it half departure. Insert. Okay, let's call this half depth for half departure. Okay, and then we will divide this by 2. Let's do that for the rest of the lines. In this example, the meridian is the horizontal distance between the midpoint of a given line and the common vertical line or axis. In this example, for our first line 1 to 2, the meridian is actually just the equivalent to half the departure, since the vertical line coincides with the latitude of 1 to 2. Okay, so now by having that, and then here the latitude for line 2 to 3, and then this is the half depth. Okay, but the meridian is from the midpoint up to the common vertical axis. So that's our interest. Okay, for 3 to 4, this is the latitude, and then this is the departure. Oh, by the way, I adjusted this 3 to 4 because, as you can see, this is the original plot. Okay. I just adjusted it for our presentations, since as you can see here, there is no room for us to show what to show the meridian and then the latitude and then departure. Okay. So going back, this is our half depth, but then our meridian is actually from longer than the half depth. So from here to the common vertical axis. Now for 4 to 5, this is our departure and this is our latitude. And our half depth is from here to the vertical to the latitude, but our meridian is only this part. Okay, from the midpoint up to the common vertical axis. Okay, moving on. For line 5 to 1, this is our departure, and then this is our latitude, and our half depth is this, and which is also our meridian, because our latitude coincides with our common vertical axis, where we reference all our meridians. Okay, so from here, to get the area for line 1 to 2, we will multiply our meridian by the latitude. Okay, this is just an overview. Okay, so this one, multiplying it by the meridian, we will see that this is the area formed. Okay, so this is covered. Let me highlight that for you. Okay, but as you can see, this portion is not actually part of the polygon that we are computing, but this one is equivalent to this portion, which is part of line 1 to 2. Okay, but how do we know if this is actually equivalent to this? As you can see from here, this is just the midpoint. Okay, midpoint. So this length is necessarily equivalent to this length, and since the angle of this is equivalent to the angle of this, since they have the same, they have the references from the same vertical axis, therefore when we compute for this portion, or this one, okay, which is the now the latitude or the height, there it is equivalent to this, and then this one, the half depth, is equivalent to this, something like that. Okay, so for presentation purpose, so by multiplying our meridian by its latitude, we were able to include this portion from the in computing for the area. Okay, so for presentation purposes, let me transfer that. Now let's go to line 2 to 3. This line 2 to 3 with its meridian, we will multiply it by the latitude for 2 to 3, which is this. So by multiplying that, this one, we will be able to compute for this area. Let me highlight that to show to you. Okay, so that's the area that is covered by multiplying the meridian by the latitude. Okay, again, just like in our in line 1 to 2, since this part is not actually part of the polygon we are trying to compute, but this one. However, this one all represents this one, but for presentation purposes, let me just transfer it here. Okay, to show that it is already covered when we multiply the meridian for 2 to 3 by the latitude for 2 to 3. Okay, Now for 3 to 4, okay, now we multiply the meridian by the latitude for 3 to 4, and by doing so we will be able to get this area. Okay, so again, just like in our previous lines, since this is not part of the polygon we're trying to compute, but it is equivalent of this one. Okay, we already computed for this portion, so let me just transfer it. Control Y. Okay, for line 5 to 5, our meridian is from the midpoint up to this vertical axis. Okay, by multiplying it by the vertical, which is by the latitude, this one, we are able to compute for the area of this. Okay, so let me highlight that. Oops. Okay. Okay. Now, just like before, this portion is not part of the polygon that we are trying to compute, but this one. But this area is equivalent to this, as we have already explained in when we discussed line 1 to 2. Okay, so for presentation purposes, let me transfer that. Now, going to our last line, which is line 1 to 5. Now we multiply this meridian by its latitude. Okay, so this one, and then by doing so we are able to compute for this area, and again this portion is just equivalent to this. Okay, so let's go directly and then shade it. Okay, this one, instead of that, we will shade this. Okay, so as you can see, this by doing the meridian method, we were able to compute for the entire area of the polygon. So now it's time to quantify everything. After we have made an overview of how we are going to use the meridian to compute for the entire area, for the individual areas, and then summing them up to compute for the entire area of the given polygon, let's now quantify everything. Okay, for line 1 to 2, our half depth, okay, let me just correct this since BBM number 1 is not included in our computation, but at least line 1 to 2. Do you remember that this portion represents the tie point and the tie line that leads to point 1 of our polygon. Okay, so much with that. Okay, so the meridian, since our meridians, as we have discussed, is the horizontal distance between the midpoint of a given line to a common vertical axis, and our vertical axis here coincides with the latitude of our line 1 to 2. Necessarily, our meridian is just half, or just equivalent to the half depth of line 1 to 2. Okay, so let's put it here. Okay, that's our and then by multiplying that, if we multiply that, we have already previously saw that that is the area for this triangle. Okay, so let's just for presentation, let's just highlight it. Okay, sorry, this one. But this one, as we have previously mentioned, this is not part of the polygon, but this one. But this one is equivalent to this. For our presentation, we will just transfer it here. Okay. Okay. And now for line 2 to 3, to get its meridian, and then multiply it by its latitude to get the area, we just need to add this one, and then add this, which is the half depth. Okay, let's put it there. less than its half depth of 223. So why do we have to reference the meridian from the previous line? It's because our line 223 actually starts from, or rather, the line 223 starts from where line 122 ends. So we have to reference it here and not from somewhere else. Okay, I hope you get the point. So again, to get the meridian, we add this one, we compute for this is the last point, and then we subtract this, the half depth, to get the distance from the meridian up to the common vertical axis. Okay, so by doing that, we will see that it is half depth of the previous line plus the meridian of the previous line, which is line 1 to 2, and then we add the half depth of the present line. Why add it? Because it's already in the negative. Okay, so this portion is now 15. Okay, so now by multiplying it with its latitude, compute for the area for this one, and then this area. Okay, this is the area that we have covered. As you can see, this one is not part of the polygon that we're trying to compute, but this one. And because this is equivalent to this, so by multiplying the meridian by the latitude, we were able to compute for this area. We have already included that. Okay, to compute for the meridian of 3 to 4, we need to reference it from 2 to 3, where 2 to 3 ends and where line 3 to 4 starts. Okay, so from there, as you can see, since this is the meridian, okay, and this is the meridian of that portion, and this one is half the depth of the line 2 to 3, we will be able to compute now for the meridian. So let's have a visualization of that. This portion is what we need. Okay, but then how do we compute for this? Is, since we got this is the meridian of the previous line, we subtract its half depth, which is this one. You remember? Okay, this one is just one half of that, and then so by subtracting it from the meridian of 2 to 3, we have this portion now. We have computed for this distance. However, we are interested on this, so by subtracting this, the half depth from this distance, we are able to compute for the meridian of 2 to 3. So just like in the previous, we just add up, since the sign of each elements will take care of the addition and subtraction. Okay, so now we have this 6.23, which is this distance. Okay, let's put it there, 6.23. So, and multiplying it by the latitude, which is this one, let's do that. This one times this one. Oops, negative. Oh, this one should be meridian multiplied by its corresponding latitude. Okay, so let's highlight this. Okay, so by computing that, as you can see, this is the area that is covered by multiplying the meridian of 3 to 4 by its corresponding latitude. However, as I mentioned previously, and I keep on repeating, this portion is not part of the polygon we're trying to compute, but this one. So for our presentation purposes, we will just transfer it here. Now let's go to 4 to 5. Okay, for 4 to 5, to compute for this meridian, we just follow the same procedure. Okay, we need the half depth, the meridian of the previous line, which is 3 to 4, and then its half depth, which is this portion now, Okay, and then this the half depth of the present meridian. Okay, so you can see this one 6.231 is measured from the common vertical axis to the midpoint. We subtract this, so we have this now, and then subtract this from the present half depth, and then we will get the present for the compute the meridian for line 4 to 5. Okay, so let's just add them up, since the sign convention takes care of the the addition or subtraction. Okay, let's highlight it. Okay, multiplying it by 1, we get this area. Okay, let's do it now. Latitude by, okay, so that's our, and then as you can see from here, this portion taken from the covered by the multiplying the meridian of meridian and the latitude of both 1 to 4, line 4 to 5, and then this portion when we computed for the area of 3 to 4, and then this portion when we computed for the area covered by the meridian 2 to 3. So you can see this portion represents this portion. How can we say that that is correct? Because this one is just equivalent to this one, and the rest, the angle, the latitude, this one, and then the departure half depth, and then this is half depth. Okay, so for our presentation, we'll just have to transfer that. Okay, as we have already observed, we just need to add the meridian of the previous line and its corresponding half depth and the half depth of the present line. Okay, so that's it. Okay, so if we're going to add this, you can see this is something like negative 15. So if we're going to add this, this should be equivalent, the difference should be equivalent to this, as you can see from our from our visualization. And then since this one, it's vertical, the vertical axis also coincides with the latitude of line 5 to 1, necessarily the numerical value should be equivalent. Although since this one is on the left side of the common vertical axis, it should be in the negative, as you can see from our previous. You can see from here, this meridian is from the left of the common vertical, so it's negative. So this one should be also in the negative. So let's see if that is correct. Okay, we just add up the previous, the half depth of the previous and its meridian plus the current half depth. Okay, so our analysis now is correct, and we have already computed for the last meridian to complete the area. So you can see from here, the numerical values are almost the same, except that there is just a 1 millimeter difference, which is very negligible. So that after we have computed the meridian, we just multiply it by its corresponding latitude. Okay. Oops, there's something wrong here. This should be negative. Okay, negative. Probably. Okay, let's highlight that for. Oh, sorry. Okay, again, for the last time. By multiplying the meridian by its corresponding latitude, this one, we were able to compute for the area of this. But this portion, this triangle, is not part of the polygon we're trying to compute. But this one is equivalent to this. Okay, so by multiplying the meridian by the corresponding latitude, we are able to also include this area. Okay, but for presentation, let's just transfer it here. Okay, so as you can see, we have covered all the areas, portions of the polygon that will make up the our lat area. So as you can see from here, there is a pattern that before that we need to add all the areas formed by multiplying the respective meridians by the respective latitude. So by adding them up, we should come up with the lat area. Or why am I doing it manually? Let's use the sum function. Okay, so that's 518, and you just have to disregard the negative sign. Okay, so from the previous, if you want to check, we have a copy of the title that we used in the previous. Okay, let me show this because I hid it earlier. Show columns. Okay, so that's the area that we copied from the title, and that's 589, and the one we computed is 589. So we have proven that this formula reflects the or is this correct? Or the area in the title is correct because we have already, anyway, so you get the point. Okay, now so by doing this, we are able to see that it is just the understanding of the meridian, the concept of meridian, and area is equivalent to what? The meridian multiplied by the latitude. Okay, so then summing them up to compute for the entire area. Okay, so that's how we do it. However, since this is the concept that we are using, okay, let me just copy this, and then show to you that this is not actually the method that we are using, but this is primarily this is the basis. Okay, or how do we derive the in actual we do not divide the departure to get the half depth. We just simply use the departure to get the meridian. Okay, but since we do not divide this by 2, necessarily the meridian, the resulting meridian is actually double. Okay, so for the first example, not that one because that is the tie point and tie line, but the second row. Okay, as we can see, this one we just copied the meridian, the departure, since the latitude coincides with the common vertical axis that we have used. Oh, by the way, you can use anywhere in your any common vertical axis that you can choose, but you have to adjust the entire figure to suit that. So for our purposes, we don't need that, but you can do that. So for example, you have a very large polygon, you can adjust it any way you like. You can use that when you subdivide a very large portion, which probably we will do on the next video. Okay, so just adding the departure and then the DMD of the previous lines, and then the departure of the present line. See, okay, so we'll do the same for the other lines. Okay, and then multiplying them again, the DMD by the latitude. Necessarily, since this is double meridian, the area the resulting area will be twice as that when we computed for the meridian and then multiply it by the latitude. Okay, so let's check that is correct. That one. Okay, let's sum this up. Okay, and then let's prove that it is actually twice. Okay, let's divide it by the meridian. and then okay, as you can see, that's double, and then for the area, okay, so this one is just the double area divided by the area that we have computed in explaining the meridian concept. Okay, so you can see it's just double. So now, this one, so necessarily the resulting area is twice that of the one we previously explained. Okay, so since that's the area, we need to divide. For presentation purposes, by the way, I just placed the formula here. Okay, so you can see this is just the sum of the entire individual area, double areas, and then divided by 2. This one, this divided by 2 to compute for the plot the area of any given title. So I hope you learned. I hope by watching this video you are able to learn on how to compute this. There are other methods that we can use to compute for the lot area, like for example using this. Okay, no, not that one. That's not part of the. So okay, times multiply by the, okay, that one, and then this one multiply by the first y coordinate, and then okay, then this one, just copy it, the numerical value. Okay, so here I just need to sum up. Okay, then we just sum this column also, and then we just take the difference and then divided the difference by 2. So you can see this one is just the same as that one. Okay, so this is another method. So I'm not sure where I got this formula. I checked the internet, but it's no, probably it is the result of calculus. I'm not sure, but I've been using that to check all my computations. Okay, so for example in this, as you can see, using that method, the last method, we're able to use this and then compute for that. You can see, okay, that's the sum, and then this one is that one, and then okay, another example is the one we will be using in on video 3, using the proclamation 133, which segregated the portion of a parcel of land from the coverage of the military reservation in Taguig. Okay, so let's check. So that one, and then okay, so that's how this one is almost 54869. So I know that this one is we copied from the, so 5486. It's almost the same, just the rounding off probably of the most likely it's the rounding off of the numbers. Okay, so that's how we compute the lot area of any given technical description. I hope you like this, guys, and then please subscribe and share it so that anyone who needs it may so that this one may help anyone who needs it. Okay, please wait for the third video, which will be all about application of the first and this second video that we have discussed. Thank you.